up in the laser industry specifically.
It has changed dramatically.
The field of biophotonics was just getting started.
The first instrument that I bought was a microwave spectrum analyzer.
It's time to shed light on our universe. This is All Things Photonics, a podcast about the physical science of light. Join us as we explore the latest in lasers, optics, spectroscopy, and microscopy. Each episode, you'll hear from leading voices from across the photonics landscape. We're brought to you by Photonics Media.
This is Associate Editor Joel Williams. Here are this week's top stories. Physicists at the National Institute of Standards and Technology measured and controlled a superconducting qubit using optical fiber rather than metal electrical wires. The work moves toward a universal quantum computer capable of solving the most difficult equations, which is estimated to require about 1 million qubits. City University of Hong Kong researchers developed a multi-wavelength optical resolution photoacoustic microscopy system based on a single laser source. The system enables simultaneous multi-contrast imaging of hemoglobin concentration, blood flow speed, blood oxygen saturation, and lymphatic concentration. Information at the level the new system is able to deliver provides subcellular insights useful for the study of disease models, such as in cancer research. A Stanford University research team developed a self-cooling laser based on a silica fiber architecture. By overcoming the need for external cooling, such as with a water-based cooling system, the design charts a course for future laser-based devices capable of delivering exceptional purity and frequency stability. Ludwig Maximilian University researchers developed an electrochromic thin-film material that, by changing colors rapidly, is poised to feature in the design of smart windows, solar energy production and acquisition, and automotive applications. The material, which relies on electricity to change colors, is part of a generation of highly ordered lattice structures known as covalent organic frameworks. These are made up of synthetically conceived organic building blocks that, under the right conditions, form crystalline and nanoporous networks. And finally, researchers led by Stefan Hell at the Max Planck Institute have developed a light microscopy method called MINSTED that is able to resolve fluorescently labeled details with molecular sharpness. The technique is derived from STED microscopy, also developed by Hell, for which he received the 2014 Nobel Prize in Chemistry. That method was able to achieve a resolution of 20 to 30 nanometers, approximately 10 times sharper than the light microscopes available at the time. The new method provides sharper images and with less noise. Up next, news editor Jake Saltzman is joined by Greg Quarles, former OSA Chief Scientific Officer and CEO of AppliedEnergetics, for a conversation about directed energy. I'm Joel Williams, and you're listening to All Things Photonics.
Today's episode is sponsored by Perkin Elmer. Perkin Elmer is an industry leader in applied markets, providing laboratories across the world with analytical instruments, accessories, services, and solutions that they need to succeed. We strategically partner with customers to enable earlier and more accurate insights, supported by deep market knowledge and technical expertise. For more information, visit www.perkinelmer.com.
Our guest today served for 6 years as the Optical Society of America's Chief Scientific Officer and is a globally recognized leader for his work with the Department of Defense and in the progression of global materials research, including new laser devices for military, medical, and industrial applications. He is founder of Optoelectronic Management Network, and he serves today as CEO of AppliedEnergetics based in Tucson, Arizona. He is a leading voice, both domestically and internationally, on the subject of directed energy, which will guide our conversation today. Hello, Greg Quarles.
Good morning. How are you today?
I'm doing well. Thank you for being on with us. So we'll jump right into a question about the field of directed energy. This is a field that incorporates so many distinct core photonic technologies that we cover here, as well as applications. You've got sensors and detectors, certainly optics, within optics, fibers, coatings, freeform optics, and certainly lasers and displays. In its most basic definition, what is meant by directed energy?
I think from the optics and photonics perspective, it's how do you put energy on a target or on a threat, such as anything across the electromagnetic spectrum. It could be X-ray, it could be particle beams, it could be millimeter waves. But in most cases, for our community, it's really about microwaves, radio frequency, and then primarily putting photons on that target. And it's to do anything from interrogating the target using photons, that is, shine a light on it, use a sensor, and detect what that target is, identify the target, to something called jamming, which is to put so much light onto a sensor that you saturate the sensor, to detection of targets, to damage of the targets, to destruction of the targets. So it's various levels of power and or energy, and it's various effects on the other end.
So with directed energy, one of the things that we talk about a lot, or that we hear a lot about, is the transfer of technology, the technology transfer. And when we talk about that through a directed energy lens, we don't really have to go very far to hit on the fact that this field draws extensively on industry and from industry and components manufacturing. And I do want to ask you about some of the seminal contributions from industry in the last 60 years or so, corresponding to the advent of the laser. But from a defense side, I want to go there first. How are we seeing the application of technology, of directed energy technology in the defense sector? Circling back to the influence commercial applications and the supply chain are having as a result.
Well, I think if you look at companies like ours, AppliedEnergetics and other companies, a lot of the research and the product development that takes place is really viewed through a dual-use lens. So you may be funding with internal research and development. You may be funding with contracts and grants from the federal government. But what you're trying to do is develop technology that takes the current technology a step forward in innovation. And so I think a lot of what's done is looked at how do we generate a technology that can be used both on the scientific side as well as on the defense side. And so, as you said, from the advent of the laser 60 years ago to today, I think a lot of the research and the fundamental transition of technology has come in the form of the components as one separate area and in the form of the laser gain media. And from the components, you mentioned some of them. I think, wavefront sensors are a really good example. One of the things that you want to do is look at how do you put the photons on the target in a way that you can get the desired effect. And typically that means putting as much energy or as much peak power on that target in as small of a spot as possible. So you need to be able to detect how the light goes through the atmosphere, what the perturbations are, and how you're going to correct for them at the laser end. That's done every day with telescopes and trying to look at atmospheric propagation of light as they do their detection. It's also being used in the Department of Defense on the lasers that are being generated. You have to worry about standard and fundamental optics such as windows, mirrors, and lenses. As you try to intersect and interrogate various targets, you sometimes have to go to higher and higher powers, higher and higher energies, and that means that you really have to worry about how well do the photons propagate through this lens, how do they reflect off of the mirror, what is the damage threshold, how do we continue to increase the manufacturing at the polishing side to get better surfaces, to how do we get better coatings on these optics so that the damage is reduced. Then it goes to fundamental technology such as power conditioning. It's used in the computer industry all the time. How do you clean up the power so that it keeps your laser running stable? How do you get rid of the waste heat? Thermal management is a really key issue that's driven a lot of the evolution of the technology over the last 60 years. And then finally, it's the gain media. How are you going to generate the photons? So it starts from everything from the evolution of diodes. Back in the 80s, the increase in the power of the diodes where you could actually pump the laser gain media, to coupling the diode light into the gain media, if that was a fiber or a crystalline solid, or in some of the new cases today, coupling the light into the alkali lasers, such as the DPALS laser. All of those really play a key role in what we've seen in the evolution of the technology over the last 60 years. And now it's getting to distributed gain. How do you pump multiple fibers? How do you couple those fibers? How do you continue to generate more power with these fiber bundles that you have instead of having 5 or 10 kilowatts? 10, 15 years ago, there was a 100 kilowatt demonstration. Now there's a goal of 300 kilowatts. How do you continue to increase that power as time goes on while continuing to worry about size, weight, and power reductions on the overall system so that you don't just have this behemoth of a platform out there? It still has to be manageable in the field.
Greg Quarles, our guest on All Things Photonics. He is CEO of AppliedEnergetics. And one of the things about AppliedEnergetics that you mentioned just a moment ago is that it's a dual-use technology company. So we're talking about supporting the needs both of industry and defense, but it's very much a business. Can you talk a little bit about the balance that AppliedEnergetics strikes between weighing, on the one hand, the supply chain and the things that you would consider with industry, but at the same time also the needs and interests of something so monumental as the defense sector?
Well, what we're consistently looking for is innovation within AppliedEnergetics. How do we generate the intellectual property? How do we come up with new ideas that can impact not only the defense sector but society as a whole? And just to give you an example, one of our primary focuses at AppliedEnergetics is looking at the generation of ultra-short pulse photons coming out of our laser systems. And when I say ultra-short pulse, I mean, something in the hundreds of femtoseconds region, less than a picosecond for sure. And what we're seeing is that, yes, there are applications and growing applications for this technology in the defense sector, but there are applications for it in the energy sector to try to get more compact tabletop linear accelerators. There are applications for it in the medical and biomedical sector in terms of trying to get a tunable set of wavelengths coming out of a laser where you can penetrate tissue and go in and look for abnormalities, tumors, things along those lines without damaging the tissue because you've got the pulse width so short. And then finally, the growth of 3D printing, the additive and subtractive manufacturing sectors are all really looking at how do I put more photons on this piece of material to either take material off or to add material to that. So, we look at each of the technologies that we're innovating and how can we apply it to the non-defense sector as well as to the defense sector, because we know we have to have a commercial market in order to sustain growth for the corporation.
As you're outlining some of all of this here for our listeners at All Things Photonics, it strikes me that this audience is not the only audience that you are articulating this to. Certainly in your time as the Optical Society's Chief Scientific Officer, and also today, you're doing a great amount of explaining this and talking about the potential of this technology to those in government, as well as those in industry. What are some of the core messages that you find yourself conveying about the potential of some of these technologies?
I think the core message has really resonated when I was at the Optical Society, and they continue today. And that is, number one, we need to have a pipeline of students. We need to have the educational system that is encouraging diversity, that's encouraging freedom of thought, the ability to bring students to the area of optics and photonics. It's such a growing field, from everything from telecom to gravitational wave discoveries to everything in between. And we need to bring really bright minds to this area, and it needs to be a diverse pool of minds. Secondarily, we need to encourage our governments to be able to put more money in worldwide to be able to establish research labs, to be able to establish a place for students to come in and become energized about making this a career path for themselves, and then demonstrate across that path that there's academia, which is important for the educational process, but there's also industrial research that takes place all across the globe. There is research within federal labs. There's research in various different areas, and including at the not-for-profit level. We need individuals in there to be able to explain science at a fundamental level, to be able to go into the halls of government across the world and bring to them in a very easily understandable form, what is this that you're talking about, and why does it impact me? Why does it impact my constituents? Why does it impact our area and our country? So we need people from science comm all the way to the fundamental researchers, and that takes time, that takes money, that takes excitement level at the STEM, at the grassroots from K through 12 to get these students energized. And then for what we're talking about here, especially within the United States, for Department of Defense work, we need students that are eligible to get security clearances. So we need them to understand what it takes to do that so that potentially they can work on programs that may be classified.
Has this message evolved over time as you've spent years in the industry spreading it to different populations? And tell me a little bit about how how this notion has grown and how the message has grown with it.
Well, I think what you see today is that advocacy and public policy are not taboo terms. Some 30 years ago, when I first started working in the advocacy side, it wasn't really looked upon as something that a scientist should be doing. You shouldn't be out there promoting the need for more funding, the need for better education at the government level, things along those lines. It was something that you had a public relations person do and not your scientific community do. And I think you'll see that many of the professional societies, whether it's in the optics and photonics field or in other fields, have started to see the necessity and the benefit of doing this public policy and outreach. It helps to be able to go in and talk to one of your government leaders and be able to describe why is laser research important? Why is it taking us 60 years to get to where we're at today? Where would we be without it? And really look at what are what has come out of funding the government in the scientific area. And one example that I've been using a lot lately is these infrared thermometers that you're holding up to your forehead as we look at measuring temperatures during this pandemic. This came out of a NASA-funded program to figure out how to take temperatures of astronauts in outer space in a confined area and be able to do it in a repeatable manner. This was a NASA-funded program that is now, in the hands of every single household around this world. And another one that I talk about is a lot of the work that has taken place with our cell phones. I mean, the semiconductors that we have and we utilize in our cell phones and computers and everything every day came out of a DARPA-funded program some 30 years ago. It was DARPA that had this vision for this really hard problem to solve for semiconductor growth. So these are the kind of things I try to express to the government leaders is this is a long-term commitment to funding fundamental science that has payoff in the end. It isn't a short-sighted game. It really has a return on investment, but it takes time, it takes bright minds, and it takes a global community working on this together in order to solve these problems.
Today, in the directed energy space, where are we seeing the majority of funding directed? And how has that shifted in the last 15, 20, 25 years?
I think, if we go back and look at the kind of the directed energy roadmap, I think back in the 70s and 80s, the most powerful lasers that were in existence at that time were CO2 lasers. And they were being developed for the industrial market space, cutting, welding, things along those lines. And those powers they were able to scale up into the hundreds to 1,000 kilowatts, but there really was no way to keep the beam shape controlled. So I think lasers have shifted from this gas laser to the other types of oxygen iodine, hydrogen fluoride, deuterium fluoride types of lasers. And then I think back in the late 1980s and early 1990s, you started to see a shift towards solid-state lasers. At the time, you had the ruby laser, which was the first laser that was demonstrated 60 years ago, and then neodymium YAG became a predominant laser. Laser glass was being used at places like Lawrence Livermore for inertial confinement fusion. And you saw a real focus on how do we use gain material that can generate these powers, but have it continue to scale up into the megawatt area and be able to do it at a repetition rate that was high enough that you could put that light on a target downrange. So I think the biggest transition that we've seen, let's say in the last 20 years, has really been because of the funding coming out of the Directed Energy Joint Technology Office, trying to get solid-state laser gain to see if it could be efficiently used in that hundreds of kilowatts to the megawatt region. So it's gone from yttrium, aluminum, garnet, YAG type of slabs and amplifiers to distributed gain material made out of crystalline plates, and now has really transitioned to fibers. I mean, we use fibers every day in the telecom area and getting fiber optics to the home. You know, with the work that was done, you know, coming out of Bell Labs and other places in developing very low impurity fiber, they were able to demonstrate that you could start putting higher and higher powers through this fiber and generate laser light from it. And now what you have is something that is reducing in size because you're using these fibers that are somewhat larger than a hair on your head to propagate light through and generate tens to hundreds to thousands of watts coming out of them. And the real focus, I think, over the last, let's say, decade has been, you know, how do we take these distributed gain materials, whether they're fiber, you know, coherently combined fiber, spectrally combined fiber, how do we take this set of 100 fibers and generate 300 kilowatts from it? How do we take that and have it have a very clean beam that you can control out kilometers away from the laser and put that light onto a target with precise targeting and rapid engagement of the target? So I really think that the biggest gains have been made from diode pumping to diode pump fibers to coherently combined fibers to this whole distributed gain where you're generating light all around your platform and then bringing it together at the output piece.
I'm really pleased that you sort of put some marks on the timeline here as we talk about this shift from CO2 to solid-state lasing that has impacted really the whole of photonics, but maybe nowhere more than directed energy. On directed energy, in terms of its weapons applications, directed energy encompasses multiple distinct types of weapons or threats, and they really span the full width of the spectrum. Can you now take us across the spectrum and hit on some of those individual threats?
If you think back to the 70s when directed energy was just kind of this twinkle in somebody's eye and the whole Star Wars concept was being evolved, it was really to try to negate the Cold War and the worry about somebody using a nuclear weapon on somebody else and launching it as an intercontinental ballistic missile. And there were thoughts about how do we or how does any other country use light or use this, you know, laser operating at the speed of light to put that light on a flying missile and shoot it down before it has a chance to do any destruction. And I think, you know, during that time frame, the CO2 lasers and the chemical lasers were really being explored to see if it was possible to do that and to propagate the light through the atmosphere and get it onto the target. So I think the ICBMs were really kind of that first threat. And then after that came other types of threats that people had to worry about, you know, more readily on a day-to-day basis, whether it be a mortar being fired or munitions, or now when you look at the threats that we have today, it's things like UAVs, drones, if you will, flying unmanned, that have cameras on them that can be weaponized, that can have explosives on them. You know, so you've got this whole gamut of current threats, and then you've got other threats that are out there. I mean, you have threats that were just really high-flying aircraft that had sensors on them, you know, whether that be cameras or imaging platforms that you wanted to destroy the focal plane array or the CMOS array, and you wanted to take out their ability to watch what you were doing. So it was, how do you propagate light up into the atmosphere to an airplane or, you know, maybe even potentially to a satellite? Those are really tricky things to do because they're moving fast. And then if we look at, you know, what are we facing today as global threats? I think the UAVs are quite a large threat. I think that things like cruise missiles, things that fly very fast that could hit, you know, the side of an aircraft carrier and damage the ship. How do you destroy that, defeat it, or at least take out its ability to intercept the target by blinding it and taking out the cameras on there. And then, I think upcoming, we hear a lot in the press about multiple countries working on hypersonic missiles. And these are missiles that are flying between Mach 5 and Mach 20. How do you shoot something at that? If you were to shoot a munition at that, how do you shoot something up into the atmosphere to hit something flying Mach 20 and try to destroy it? It's really hard. You've got to be able to track it, and these things are programmed to be able to move. So, your best solution may be the use of photons going at the speed of light and intercepting that target, tracking the target and trying to intercept it and damage it before it reaches wherever it's intended to go. So I think what you're looking at is, what is this threat? How quickly does it move, and how do you engage that as it moves quickly? And what we see is that engaging anything at the speed of light gives you a better opportunity to destroy that. And so now you need everything that's wrapped around it to give you relatively low operational cost and logistic support, and the ability to have a wide area of coverage to look over the horizon, to look in the sky, to look underwater, and then be able to take care of that threat.
So these increasingly high-power systems, and specifically laser systems, are certainly under development for a reason. And I know you touched on this just now in that last answer, but what are some of the other types of threats that engineers today and systems developers are working to address, be they in application now or perhaps horizontal?
I think some of the things that people are looking at are, how do you disrupt a platform with the least amount of damage? So, if you have something that has potentially a high value to you, that maybe it's got data stored on it or whatever, how do you intercept something that has a computer or communications or some other type of electronics on board without destroying the whole platform or taking human life? How do you make this non-lethal, but you're able to shut it down? So, if you think about it, one of the things is you have drones that fly in the air, and a lot of times they have surveillance equipment on there, and you may like to take a look at what they've been recording to understand what they're watching that you have. So your preferred method would be to be able to bring the drone down onto the ground and look at the equipment that's on board. Now, you could try to shoot it out of the air with a missile, you could try to shoot it out of the air with something else, but at that point, you've completely destroyed it. The mission's accomplished. You've taken it out of commission, but you don't have the ability to interrogate it. So if you can use radio frequency or microwave, or if you're able to use an ultra short pulse laser where you hit the side of the platform and that optical energy is converted to radio frequency, and now you've damaged electronics and it can no longer fly and comes to the ground. I mean, those are the type of things I think that engineers are really looking at, is instead of just having a hard damage to the system, how do you do soft damage to it so that you can be able to look at it in the future?
I want to get some insights from you now. I mentioned your past as, for 6 years, serving as chief scientist, the Optical Society of America, and just to be a fly on the wall for some of those conversations would be absolutely fascinating. Certainly can't do that now, but how do you reflect on the experience now 5 years after your appointment? Was the tenure what you expected, what you hoped, all that it would be?
It was tremendous. It gave me the opportunity to work with thousands of scientists around the world that were doing cutting-edge research and technology development in all areas of optics and photonics. My specialty was in laser materials and directed energy and things along those lines from my previous work. But like I said, this gave me the ability to be in DC to witness the announcement of the first detection of gravitational waves from the LIGO group, to go out and visit LIGO out in Hanford and to go to their ESA Virgo facility over in Italy. It gave me the opportunity to meet with scientists that were doing some of the best work in optical imaging and microscopy in the world. It gave you the chance to sit down and ask questions and hear presentations and help to stimulate the ability to bring students to this field that just have a magnificent amount of energy. It gave me an opportunity to take part in really an expansion of diversity and encouragement and inclusivity in our field, to bring it to where we have multiple voices sitting around a table that can express their input from directions that, I may not have had from directed energy or laser materials. So it was really a fantastic opportunity to talk to everyone from undergraduate students to the multiple Nobel Prize winners in optics and photonics, and really hear their life story, where they were going, what was taking place, and to celebrate what's taking place around the world. I mean, to celebrate the Nobel Prize that took place with Donna Strickland and Gerard Moreau, ultra short pulse and high peak power lasers. And those are the kind of things that are type of once in a lifetime type of opportunities to experience, and to do it with 26,000 of my nearest friends in the Optical Society was very uplifting. And also, it was an opportunity to travel the world, to talk to global leaders, either at the EU or throughout Asia or South America, other continents, to understand what their challenges were. I had the experience to be able to go through and visit leaders through multiple countries in Africa that were really trying to find a path to being able to attract better talent globally and bring them in to help their country, their universities, establish optics and photonics centers. So those are the kind of experiences that will last a lifetime, that made lifetime friends and colleagues, and really forced me to learn more about what was taking place. And then you see things such as the revolution and the breakout here in the quantum computing area now. To be able to be a part of that and to sit on the National Photonics Initiative and National Quantum Initiative panels and help to drive that in front of our congressional and executive branch leaders, as well as university and industry leaders, and really accelerate the funding and the acceptance of that as a technology that needed to be high on the list of breakthrough technologies for our country and for the global world, and talk about the use of optics and photonics in those areas. Very uplifting, very, very exciting.
So no doubt there's a global optics and photonics community, but I'm curious about potentially a global applied or directed energy community. No doubt there are constraints in the sharing of information. Those things are of natural consideration within this area of photonics. But is there, in your mind, a global applied energy community?
There is, and I mean, you look at some of the global leaders in optics and photonics. Thales and BAE are both European companies. There's a tremendous directed energy community in Israel, and I'm certain that China and Russia have directed energy communities that have regular meetings. Again, there are constraints there, but there are some global directed energy meetings. Obviously, the ability to attend is somewhat limited, but there's a strong UK and EU position in that area. And again, I think it goes back to the dual use. If you look at the expansiveness of the E-Light program and the beamlines that have grown in Europe to really do high peak power fundamental physics with lasers, and you look at the work that takes place in Europe in the high power CW systems from places like Fraunhofer and DESI and places like that are going into the industrial sector, into cutting and welding and via hole drilling. All of those bring light to the application, not only in industry and not only in fundamental science, but also to the directed energy side of the portfolio. So there are researchers that are working in that area all around the world.
What are some of the misconceptions, or maybe a better way of saying it, misunderstandings that the public has about directed energy beyond just what it means and where it's going? And I suppose the second part of that is, are there ways that we or those in the media can better cover advances in the field?
I think the biggest misconception that I've had questions brought to me with is, are you using this on humans? And, I think that's the biggest erroneous part from the sci-fi movies of the 60s and 70s. There is a rule within the Geneva Convention that you are not allowed to have this be lethal or damage eyesight. And so, many of the directed energy researchers in the community worry very much about, is this an eye-safe optical source? How do we, maintain eye safety at all times? I mean, the last thing you want to do is blind somebody that's one of your allies. And it's illegal to blind people in the field. So, I think that's the biggest misconception is you're not shooting a death ray at somebody and killing them with a laser. And you're not blinding people with lasers. Those are completely forbidden. I mean, what we're trying to do is to deter technology from being used on populated areas and on civilian population by intercepting the threat at the speed of light and damaging it or destroying it. It's as simple as that. So those are the types of breakthroughs that we're trying to make and trying to have out in the field so that we save the lives of our men and women in the armed services and we save the lives of civilians.
In the last, it looks like 13 months, if my math is correct, we now have a new branch of the military. Perhaps the way it was announced was not in such a way that the focus is on the technology more than anything else. I'm talking about the Space Force there, but drawing from the insights you've shared with us on the podcast here today, what looms next for directed energy and maybe within that high-powered laser applications?
I think the biggest areas right now that are being funded and are really being looked at are how to defeat swarms of things that are flying fast, whether those are mortars or missiles or drones, because with the evolution of other areas of technology, such as artificial intelligence and machine learning, if you look at things like some of the programs, sporting events on TV, and you see these magnificent drone displays with flying LEDs and lights and formations and movement through the sky, you can see how these things can operate remotely and be controlled as one unit. So I think one of the big worries globally is how do we defend our airspace and how do we defend our commercial airspace? You look at the shutdown of Heathrow several years ago and the billions of dollars that were lost because somebody was flying a hobby shop drone around the airport and they had no way to intercept it or destroy it or take it down. And therefore, aircraft had to divert to other airports or be sitting on the ground and not be allowed to take off because this was a threat to, being sucked into an engine and damaging or making a plane potentially crash. So, I think trying to understand how you can use light to solve problems like that impacts both the commercial and the military sector. And then, as I said previously, I think former Secretary Esper had said last year, he foresees one of the biggest threats emerging globally as the hypersonic race. And this may be the next arms race, if you will, because you could launch a hypersonic missile that's going to go Mach 20 and then go completely across the Pacific Ocean in less than an hour. That's not a lot of time to react to a trajectory of a missile coming at an unknown target. So I think coming up with ways to be able to intercept those types of threats using advanced optics and photonics is going to be one of the higher funded areas coming up here over the next decade.
Greg Quarles is CEO of AppliedEnergetics. He joins us on all things photonics from Tucson, Arizona. Greg, thank you for being on with us. Stay safe and all the best to you.
Thank you very much, and the same way to our community out there. So thank you for the time today. I really appreciate it.
For the first time in All Things Photonics, we have the chance now to explore the topic of optical power beaming. You might be familiar with the terms power over fiber or free space power beaming. And in essence, what we were talking about is the transmission of energy via optical fibers in the form of laser light. Applications for the all-optical technology span those in telecom datacom to monitoring via UAVs and UUVs. A leader in the space is PowerLight Technologies, located outside Seattle, and the company's co-founder and CTO, Tom Nugent, joins us now. How are you doing, Tom?
I'm doing very well, Jake. Thank you. How are you doing?
I'm great, thank you. So I've described it a little bit. Certainly you're more and better equipped to do it than I am. What is optical power beaming, and why now is the technology advancing?
Optical power beaming is a way of taking electrical power from somewhere where it's easy to generate and gather and transmitting it to somewhere else where it's much more difficult to have that energy. And we do this by taking electricity and converting it into light with a laser, and then projecting that light either through the air, which we call free space power beaming, or through an optical fiber, this power over fiber you mentioned, where at the other end, specialized solar cells convert that light back into electricity, where it can then be used to charge batteries, power devices, and do whatever else you need an extension cord to do.
So you've described it as a system of systems, and it really is just that. And we mentioned telecom and datacom. And when you're a technology company, or any company really, a startup or spin out or anything, one of the focuses has to be on identifying the optical nearer term adopters. Who's going to benefit most from the technology and quickly? What industries have you identified as possessing the highest value in terms of implementing this technology?
You're right. And it's been a number of years talking to a lot of different potential customers to narrow down to the ones that make sense for the first products. And the telecom industry and the military are the ones we're pursuing right now. Telecom has a lot of need with the deployment of 5G to be able to put up a lot more telecommunication nodes rapidly. And the permitting process or the process with getting new power lines run can slow that down a lot. So there's a lot of interest for them. And on the military side, of course, there's always a need to move fast or put power into places such as unmanned aerial vehicles, where it's really hard to run a power line in any other way.
Take us through the journey, the advance of the company, its origins, and how it's arrived to its current point in these conversations with telecom, datacom, and these military firms.
Yeah, we got our start, 14 years ago. My co-founder, the late Dr. Jordan Kerr, had been working with lasers since he was in high school in the 70s, and had in the 90s looked at different ways of using lasers for power beaming and even for launching rockets. I met him in the mid-2000s, and we wanted to make a commercial go of using power beaming for initially niche applications. And we got our start coincidentally when NASA was offering prize money in their Centennial Challenges program for power beaming. And that was a competition where, in the context of the competition, you had to have a robot climb a cable to 1 kilometer in the sky, powered by nothing but power from the ground. And we won that in 2009. And then a few of us on the team quit our day jobs and started from there, and have been working on improving the technology and a lot of the different subsystems and understanding these market needs ever since.
Tom Nugent from PowerLight is our guest. Safety and utility, they're always going to be among the areas of concern, or at least thematic to a conversation when you're talking about the generation of power. How's optical power beaming, and within that PowerLight, addressing those challenges?
Yeah, and one thing to say about all of this that I think a lot of people listening may not realize is just how close this technology is to reality. And one part of making it real is to make it safe. You can't really offer a product that's not going to be safe. And when people think about lasers, they think of death rays and pencil beams. And what we have been doing is making active sensing as well as passive design features that make it so that no one can be exposed to the hazardous levels of light. And it's analogous to the insulation on electrical wires that are in your house. You know, you could hurt yourself with those electrical wires, but insulation and GFI circuits make it so it's safe. And we're doing the same thing with these different active sensing technologies to be able to shut the laser off temporarily before anything can get into the beam. And then it comes right back on after the beam path is clear. And since there's usually a battery or some energy storage at the other end, it allows the device that's being powered to have uninterrupted power, even if the power beam has to shut off occasionally for these safety concerns.
And one of the interesting angles, I suppose, that you and your company here are working throughout, are navigating, is the fact that you have the technology, but in many ways, it's not so much the application that you're concerned with. It's an interesting dynamic. I'm just curious, tell me a little bit about that dynamic and the ability to work throughout different applications and how the process of identifying the right ones goes.
Yeah, no, it's a good question. And what we are effectively offering is a wireless extension cord. So as you can imagine, anyone who needs power has come to us over the years and asked, can you power my device? And the answer is generally yes, because we're just delivering electricity. It is in many ways like an extension cord or a USB cable. And so the challenge is given that this is a new technology and has some components whose prices have been falling, but which are still high, trying to identify which of those use cases can accept the initially high price before the quantity scales up and further drives the price down. And who understand that as a new technology, there will be kinks to work out. And so it's been really great talking with people in the telecom industry and in the military as we do demonstrations of systems with those customers, getting their feedback on the facets that are useful to them. We don't want to take this analogy too far, but it's sort of like, iPhones or cars or whatever. Before people actually have it, they don't really know what they want. And so it's important to get these systems to them to use for them to then explore and understand really what are the important factors beyond, of course, the basic, we need X amount of power over Y amount of distance.
It's really a fascinating dynamic, and it raises an obvious two-part question, and I hope we can end with it. Number one, how close is PowerLight to a product rollout, and what is that product?
So we are targeting having a product in customers' hands for early deployment in approximately 2 years. And that depends on a lot of factors, but we are working through all of the different aspects necessary to get there. And that first product will be this free space wireless power system that will deliver somewhere in the order of 0.5 to 1 kilowatt of power over a distance from probably 0.5 to 1 kilometer. And that's one of the things that I think sets us apart from other people working in the general wireless power space, is that we're focusing on much longer distances and higher power levels than just about anyone else. We have demonstrated all of the necessary subsystems and capabilities, and are now iterating it through, as Elon Musk has called it, the production hell. We're getting closer to that of taking what has been demonstrated and making it robust and reliable and easy enough to have anyone be able to use it.
And one of the things about this technology is that it's really close. Can you tell us about some of the progress that has happened and continues to happen as this moves towards a launch and a realization on the market?
Yeah, and it's still surprising to us after a number of years when we talk with potential customers or people who come out to see demonstrations, that people who are involved in high technology and finding out new components and technologies for these customers still don't know about this technology or realize how close it is. And so, as I mentioned, we've been developing all of the different subsystems to make it be able to deliver the power that's needed at a reasonable efficiency, and being able to make the safety reliable and reliable enough to be certified by third parties to be safe. And all of that has been coming together and now integrating and, making the transmitter and receiver ends smaller and easier to manufacture. And all of that has been coming together over the last few years, such that we expect that this closer than you think fact is really going to hit people home over the next couple of years as we get this out to field deployment.
That's Tom Nugent. He is co-founder and CTO of PowerLight Technologies. He joins us today on All Things Photonics from just outside Seattle. Tom, thank you for being here.
Thank you. It's my pleasure.
That does it for this episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to Joel Williams with the news. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website. Subscribe, never miss an episode. I'm Jake Saltzman. This has been a Photonics Media production.